Good morning and welcome to the 7th edition of AETalks. My name is Peter and I'm part of the Advanced Engineering team. Today we're hearing from Joe Armstrong from Polytec. Joe will be taking us through some of the primary benefits of optical surface metrology to explain the when, where, why and what of the subject. I'm sure there'll be a lot of engagement throughout, so before we get started I'd like to go through some housekeeping. On the right-hand side of your screen, you'll see a chat function, a questions function, and a polls function. Please say hello, add comments, and share tips and opinions in the chat function. The more engagement, the better for everyone, really. It does make a slightly annoying pinging sound, so you can mute this by clicking on the audio button at the top of your screen. If you're having trouble finding this, it looks like a little bell. For any questions, please make sure these go into the questions tab rather than the chat tab. This makes it much easier for us to see them and therefore provide you with the answers. The questions can also be voted up the list so that the same ones are not asked multiple times. Joe will look to answer your questions following his presentation. We have some polls which will be asked throughout, so look out for these in the polls tab and make sure you answer them there. Joe's contact details will be posted in the chat, so if we don't manage to answer all of your questions today, you will be able to contact him directly after the event. So, without further ado, I'll now hand over to Joe, and I'll see you at the end for Q&A.
Hello everyone, my name's Joe Armstrong. I work for Polytec and I'm responsible for supporting and promoting optical metrology tools for Polytec, and today I'm giving a little talk for an introduction on non-contact surface measurements by Polytec. So I'm going to begin with a short introduction on Polytec. Polytec as a company has been going since 1967. We started with optical instrumentation, and of course our first laser Doppler vibrometer we launched in 1987, and this is our biggest product line, and this is the product line that we're most famous for. Our first steps and breakthrough into optical surface metrology was in 2004, and in 2017 we celebrated 50 years as a company. So today, our webinar goals are to give you a quick introduction to optical metrology from Polytec, talk about our technology, coherence scanning interferometry, a brief introduction on our products and applications, and some example case studies, conclusions and questions. So to begin, surface metrology by Polytec. So why surface metrology? Well, different surfaces have different functions and different performance. Surface topography has an effect on a wide range of properties, such as formability, friction, wear, visual appearance, bonding behavior, coating, corrosion, fatigue, sealing capacity, electrical and thermal properties. So surface metrology as a feedback mechanism for industry will provide you with important information which will allow you to relate and control your manufacturing process to the function of the surface. So typically within industry, the most popular method of surface metrology is a contact method, so the starless. So this method involves taking a point contact to the surface, touching the surface, and then scanning across the surface. This particular method is popular, it's traditional, and it's very well understood. So why change from starless metrology to optical metrology? The first answer is some materials require non-contact measurements, such as soft materials like rubber or materials which could be marked. So one of the benefits of optical metrology is you do not touch the surface, so you cause no damage to the surface. Of course, aerial measurements have become faster and easier. And it's worth noting that in the world of research, optical metrology is now becoming dominant. And one of the reasons it's becoming dominant is you see your surface. You get more information. So this leads us to the third answer. And the third answer is it's this human eye interaction. We look at the surface, we see the surface, we can see the lay of the machining marks, we can see scratches, we can see defects. We can do pattern recognition in a way that machines struggle to do. So to do work such as failure analysis, optical metrology in an aerial measurement format gives us valuable feedback. So Polytec now has a family of products. We have our very popular ProSurf products. We have our newly launched MicroView products. We have inline surface metrology options. And we have our introduction product, the MetroLab. So we have a complete solution from micro to macro. And I'll talk a little bit more about micro to macro in a minute. But interestingly, all our products, we have a Z resolution to the sub-nanometer or to the nanometer, irrespective of what technology we use, whether it's macro lens or micro lens. And this is due to how we signal process our data. So all our data, we signal process using coherence scanning interferometry. So we refer to this technique as deterministic. It allows us to go beyond the diffraction barrier of light, and it gives us high Z resolution and high sensitivity to a surface. So how does this work? Well, it works by we capture a data stream in Z. The data signal you see is the corellogram information. And the corellogram information we have for every single pixel on the detector. So if the detector has 1 million pixels, we get 1 million of these tiny optical probes touching the surface. As we change focus, we see the constructive and destructive interference signal coming from the white light interferogram. We then signal process the phase information contained within the corellogram, and by signal processing this information, it allows us to identify the best focus, the sharpest focus information. And this is how we achieve deterministic Z sensitivity in Z. So why aerial measurement? Well, first of all, you see a surface. So by looking at your surface, as you can see here in this example of 15 nanometer scratches on the surface, you can see the scratches very clearly. Of course, this technique is non-destructive, so non-contact measurements. The technology we use, coherence scanning interferometry, is very robust, and many of our customers are industrial, so we've become stable, reliable, and repeatable. And of course, you analyze over an area, so not just a line. So you have a greater overview, stability of the measurements in terms of X, Y, and Z. And of course, our technology has been both well accepted in research and development, as well as manufacturing settings throughout the world. And of course, we can measure a variety of materials, whether they're rough, smooth, shiny, dark, bright, light, dull, rubber, matte, all sorts of materials we can measure. And of course, importantly, all our Z data is deterministic in Z for our signal processing of our corellogram information. So we have two main product types. We have the microscopic and we have the macroscopic. So people always ask me, how do I determine what I want to measure? And my first advice is always ask how big and how small. If you consider the microscopic, then your XY sampling optically is from 0.46 micrometers. Your digital point-to-point spacing comes from 0.06 micrometers. So you're actually oversampling. If you then consider this to the macroscopic, this has a different XYZ capability set. For example, you get the longer standoff distances, up to 83 millimeters. You then have the longer scan ranges, 70 millimeters. And very interestingly, you get the much larger field of view than what a microscopic system can offer. So a single field of view, you can capture up to 45 millimeters in X. And if you do image stitching, it's very much easier to achieve measurements over 200 millimeters. So what are the differences between large area, macro lens type systems and microscopic lens systems? Well, the first main difference is your XY sampling rate. Clearly, you're squeezing more light for a microscopic system. Therefore, you're going to have naturally a higher XY sampling rate. In macro lens, as you can see, the light is more telecentric. It has a lower numerical aperture. This has the advantage of a larger field of view. However, it has the disadvantage of a lower XY sampling rate. The other differences you'll notice is the microscope lens has to be much closer to the surface. And this is due to how you're turning the light. So the light is turning much faster. That means you can measure high sloping surfaces. If the surface is mirrored, you can maybe measure 40 degrees of high magnification lenses. If the surface is specular or scattering, you can maybe measure 80 or 85 degrees slope capabilities. Interestingly, you can have similar effects with a telecentric lens. So because of a low numerical aperture, if you're measuring a mirrored surface, then you can probably only measure 2, 3 or 4 degrees of slope. However, if you have micro nano scattering generated from the surface, then you can actually go and measure cone angles, which could be 60, 65, or even maybe 70 degrees. The other difference is when you're measuring greatly recessed surfaces. The telecentric lens has a very good penetration into the surface. So you can measure large, deeply recessed surfaces without the risk of damaging or crashing either the lens or the sample. So there are some conceptual differences and practical differences to how you may want to tackle a measurement. So clearly the most obvious is when you want to measure larger areas, the microscope has to do image stitching, whereas a macroscope system will naturally capture larger areas fuller in one measurement capability. So how do I describe this? Here on the left, we have an image of a microscopic image. If you look very closely, you can see the fine texture. You can see in great detail the step information. We can see that this surface is smooth, rough. We're seeing a lot of information very close up. It's like looking at the grass on a football pitch. Whereas when we look at the image on the right, where the red arrow is pointing, you can see we can zoom in and we can see the same small microscope area where you've got the fine details, but we can't quite see that sort of leaves on the tree. What we're seeing is the penalty spots of the football pitch. We're seeing the goal lines. We're seeing the lay of the land. So the macroscope gives us a more global view of the texture. It gives us a more overview of the form, a more organic view of the step, but you can still, as you can see, get some impression of the texture of the surface. So the microscope and a macroscope are giving you access to a different range of spatial frequencies, and both can be very useful. So what do we want to measure at Polytec? Well, we want to measure form parameters. So here you have a measurement of a wafer bow flatness. This would be measured with the ProSurf product. If you want to measure dimensions, such as large steps or sealing surfaces or intersurface relationships, maybe a macroscope is more advantageous because it's giving you a global view of the surface. Of course, if you want to see small steps in great detail, maybe the microscope type system is more advantageous. Especially if you want to see the texture information. We can measure texture, and the higher spatial frequencies of the microscope will allow you to see the texture. I've made one mouse button click too quickly. So for tribology, defects. So if you want to see material removed, see shape, then both the global view and the microscopic view can prove useful for the information. Finally, in Polytec, automation. Most of our sales of our product go into automated industrial settings, especially the macro type stuff. And our automation has become very sophisticated. If you consider the large field of view and you want to measure flatness of multiple parts or key parameters, then providing they fit within a single field of view, the macro lens makes measurements not 1 times faster, but maybe 2 times faster, or even faster than that, depending on how many objects you have. So a quick introduction to our new TMS 1400, our top Mac MicroView product. So this is a microscope-based product. As you can see, you start off with the measurement head. The measurement head has a 100mm Z range, and we have this very ingenious continuous scanning technology where position equals measurement. So if you want to do 100 or 200 or 300 micron scan, if you're in position 0, it can do that. If you then move the Z stage up 20mm, it can then do that same measurement in a different position. And it can even scan maybe 1 millimeter or 2 millimeters, and it can do that throughout its whole range. So this is the explanation of the continuous scanning technology. And this is for our standard measurement tool. So as you can see, it's a tabletop version. The electronics are integrated into the system. So it's very tidy. You just have the head, you have the stand, and then you just need the external sort of monitor, keyboard, mouse, and the monitor is actually built into the back of the monitor. So it's a super tidy, compact configuration. The turret is 5 positions. We have this additional hardware option. So instruments of this type normally come with sort of some kind of pre-scan autofocus to allow you to find the surface. We have additional software to offer you an enhanced focusing capability. We have built into the system focus tracker so you can follow your surface. So this really complements automation capabilities. Of course, stages can be motorized or manual with tip tilt. Importantly, the tip tilt is built on top of the XY stage. So if you have to tilt your sample, you're always then moving the stage orthogonal to the measurement head. And all our data sheets and our specifications refer back to the FAIR data sheet. So Polytec are actively involved in trying to offer comparable specifications that are traceable to international standards through the FAIR Datasheet Consortium. If we go to our TMS 2400, this is referred to in Polytec as the MicroView Plus. This is our more advanced type configuration of an instrument. The first thing you'll notice, it has a much more open architecture. So the open architecture allows us to put different stage configurations on. We have more flexibility. We can put spacer bars. So you could put anything potentially under this instrument from maybe engine cylinder liners to small semiconductor wafers. There is a huge bandwidth potentially available for this instrument format. The measurement head is now closed loop. So what we mean by that is we have a linear scale feedback mechanism built into the head. So that improves the measurement uncertainties of the instrument. So now when you are doing large step heights, small step heights, you have a much greatly improved large step height repeatability and reproducibility with greater integrity. And again, this is all backed up with our continuous scanning technology. We now have added to this color information capability, so we can offer color representation onto the data. Again, you've got the turret, you've got stage options, and we've got the fair data sheet. So the types of microview applications we like to address are surface coatings, textured materials, micro parts and optics, precision machining, material science, and micro-macro devices. Here we have an example of Z resolution. The Z resolution you can see is to the sub-nanometer. We have an example measurement here. If you look on the profile line, the scratch is in the order of 500 picometers, so half a nanometer. At this quasi sort of atomic level, we always ask, are we measuring a real function of a surface? With the human eye pattern recognition, if you measure, move 50 microns, measure again, and the patterns move, and then you remeasure the profile lines, if you get repeatability, then you can say, I am measuring a real function of a surface. So you can get a good indication of whether we're seeing a real representation of a surface. And that's exactly the exercise I went through on this particular surface. Of course, we can measure small steps. Here's 10 nanometers. You can see the detail and the clarity of the data. And if you're trying to measure tribology, and the image on the left here is a standard pseudo color surface representation of a corroded surface. The data quality is very nice and crisp, but it's a little bit challenging to see where the corrosion starts and ends due to the nature of the pseudo color image of the surface. If we add the color overlay to this data, now we can see very clearly through color differentiation where the corrosion starts and ends. So this is a very nice addition to our metrology capabilities for failure analysis work. I've just had a flag saying that the polls are open, so I should encourage people to vote. So please vote. Moving on, as mentioned right at the beginning, we consider our premium product the ProSurf. This has been a super seller for us here at Polytec. It has the long ranges, it has the large standoff distances, it has a large field of view, and the question is, why is it always been such a winner? It's the measurement repeatability and the noise performance. So in this macro lens system, we're using our coherence scanning interferometry, which allows this instrument to get down to the nanometer in Z. We achieve this because inside this instrument, we're not using a servo motor, we're not using a stepper motor, and we're not using a piezo device. We're using a floating magnetic drive. It's just like a Japanese train, if you can picture it. So it's a low friction force surface. So that supports the sensitivity of the coherence scanning. It also supports very high step height repeatability. If you're measuring a large step height, and that step is 5 millimeters, 10 millimeters, 50 millimeters, you can achieve a measurement uncertainty on that measurement that could be good to 1 or 2 microns. The performance is really excellent on large step height performance. So the types of application we address with the ProSurf is fast large, wide area measurements, hard to reach surfaces. This is the property of the telecentric lens. You can measure multiple parts at the same time. The long working distances, the large standoff means that you're at a greatly reduced risk of crashing. You can see there's no lenses like on a turret or the microscope. And of course, large scan ranges. The one downside to this product is the lower XY sampling rate, but we've addressed this by having the optional multi-sensor roughness probe, which you can attach to this instrument. And that works really, really very in a tidy way. So you simply capture your TMS topographic data, you draw a profile line, everything is calibrated and interconnected, you click measure, and it then goes and captures your roughness, high spatial frequency with micron sampling rates, and that really extends the spatial frequencies available from this particular instrument. So for the wide area macro type applications, ceiling surfaces, some representation of roughness and waviness, multiple measurements in one field of view, measuring very challenging large area surfaces for tribology. For industrial applications, complex structures are perfect for us, and also macro shapes and components, such as these watch parts. So a couple of case studies, just to keep everyone going. Additive manufacturing is very popular. This particular example set is from the ProSurf as measured. And as people are sticking typically 20 micron spheres onto a surface, melting them, if you consider the XY performance of the ProSurf, optically this is from 8.4 microns, pixel to pixel sampling is from 14. So you have a pretty good match for the smallest things you may want to measure. So if you consider how big, how small, say I've got a pretty good match up there. And of course, one of the challenges in additive manufacturing is as you print surfaces at different angles, to control the nature of a process, then you will very easily see different textures generated at different angles. And you have to try and learn and control these different textures at these different angles. So within Polytec, all our parameters conform to ISO 25178-2, ISO 4287 and ISO 4288. It should be noted that my colleague Wilfred Bauer is the lead write-up for the ISO committee on the aerial parameters, so 25178-2. So Polytec is actively involved. Surface topography, if we consider surface interaction and function cannot fully be characterized by a single line or a profile. So aerial measurements allows us to see a greater distribution of the surface and its function in both X and Y. We accept that profile technology, especially stylus, is very well understood and established. But the example on the left, you can see it's considered a complex surface, and the texture in X is different in the texture in Y. So if we really want to fully understand this surface, the value of aerial measurements can be accepted and recognized. On the top right of the screen, you can see we've got a wear scar, and to see the peaks and the valleys of this surface, then the aerial allows us to see much more fully how this surface looks, feels, and is measured. So any measurement and analysis of a profile, no matter how well it can be done or achieved, will never fully describe that surface interaction and that surface over an area. So you'll always gain more information through aerial measurements, and it's far more comprehensive. So if we compare small area to large area, It's always very interesting to ask, especially when you consider complex structures like additive manufactured surfaces, when does shape become texture? On the left, I have an image as measured by the micro view. This is a challenging surface. It's smooth, it's shiny, it's rough, it's dull, it's high sloping, it's lumpy and bumpy. I would suggest the image on the left is shape. If we then go to the right, again this is an image from a micro view, and now we've stitched a slightly larger area. And we can see now we're starting to see some stabilisation of the general lumps and bumps on the surface. But again, is this a stabilised image where we can use a roughness parameter to give us feedback on our manufacturing process? So if we take a step back and we go, the image on the left is the leaves on the tree, the image on the right is the tree. So here we have the leaves, here we have the tree, and here we have the woods and the forest. So the images on the left is the microscope system. The image on the right is a macroscope system. So the macroscope gives you a more global view of the surface. And you can see how these technologies complement each other. So if you want to consider a complex surface, and this particular image is as measured by the macroscope, you can see I've got measurement area 1, measurement area 2, measurement area 3, and then all of the surface. And you can see I've got different parameters for each of the surface. Which one is right and which one is wrong? Well, they're all correct and they're all representative. And it all depends on how close or far away you look from the surface. And this can lead to confusion when trying to offer quality control. But clearly, seeing more of the surface gives you a greater consideration to the behaviour of how that surface is made, generated, and looks and feels. Of course, there are some guidelines within ISO, and if you have a rougher surface, and I accept that you can have a departure from the recommended ISO, but here you can see that if you are measuring surfaces typically between 2 and 10 microns, ISO are recommending that you offer a 12.5mm sampling length. So within one single measurement, the macroscope can measure a large area, and you can see I've trimmed this data set to represent 12.5mm, and that's one measurement in one go. A microscope type system would have to do a lot of stitching. So the time saving for the macroscope, if you have good representative data, could be good enough for acting as a roughness indicator for these very complex surfaces. Here we have a roughness artifact. This was as provided by a university. You can see the low spatial frequencies and you can see the higher spatial frequencies. So you can see this is a complex surface. And just to try and show where the macroscope and the microscope are over crossing each other in terms of texture capability, I've got different textures here, and you can see the ticks indicate where the macroscope is offering very good representation of the texture. And it's only when you get to the very fine spatial frequencies where the microscope is crossing over and taking over. So again, it's all about how big and how small. The lines on the bottom giving you an indication that if you had a 2D point profile measurement, the scan range needed, as recommended by ISO, for each of these surface types. For number 11 and 12, ISO is recommended, because these surface roughness is very high, you need a 40mm scan length. And of course, I've had to zigzag the line across these surfaces, which is pretty impossible to do with a stylus type instrument. And of course, if you want to measure form, then it can be extremely difficult due to the range, the size, and the nature of a surface to measure form with a microscope, especially when you have large Z ranges, large XY ranges. For this particular sample, I could get some texture information with a microscope, and I started to think about how I was going to measure this for form, and I simply decided the macroscope was the way to go. And here you can see, I can see a very challenging surface. The total height of this surface is over 1 millimeter in Z, and it's in the order of 50 millimeters in the Y direction. So conclusions, and this is the last slide and the end of my presentation. So microview brings a very nice performance to microscopic instruments, skinning, continuous scanning technology, ideal for small steps and textures. The ProSurf, very good for large areas, good for flatness, large steps, or measurements. All our instruments offer standards, and we offer very nice automation. Thank you, everybody, for taking the time to listen to me. I hope that's been an interesting presentation. That concludes my presentation. I think I'm open to questions.
Perfect. Thank you. Thank you very much for that, Joe. Most appreciated. We have a few questions that are lined up, and I'd encourage people to add any more you have now. Just before we do that, a quick reminder that there are a few polls in there which would be very useful if you wouldn't mind doing those. It's literally a one-click thing. A poll asking you the question, how useful did you find the session, which is always good for everyone to know. So moving into the questions element. So the first one we have from Mark Catchpole. He has asked, can you measure screen printed inks?
I have measured screen printed inks. On the MicroView Plus, if there's colour information, we can also extract a colour representation of those inks as well. So that's quite a nice feature. If these inks are transparent, so non-opaque, and you can measure through them, if they're complete coatings, then we can get, for thick thin films and thick films, we can get thickness information. And interestingly, the microscope and the macroscope, they have slightly different behaviours towards the nature of what sort of thickness you can measure. So if it's thinner, then the microscope's quite good. If it's a bulk material, such as, say, a thick glass, that could be, say, 5 millimeters, then interestingly, the macroscope can measure those types of thicknesses and get signal back just by the configuration of the optics. So it's worth trying to investigate both products to see which one's going to prove most suitable. We have actually measured, when we signal process the correlograms, up to 8 different layers of surface. That has been possible.
Perfect. Thank you. The next question from Terry Hoxton. Simply, what's the light source?
We're using a green LED. I think it's 514 nanometers. So this is why I would say our optical performance on the microscope is really starting in the half micron region. You can see that reflected in our specification. So the 100x lens gives us 0.46 micrometers. But we've optimized our camera sampling, so you can oversample, you can apply filters and enhance the noise performance by adding an S filter to your data. So you've got plenty of bandwidth there.
Brilliant. Going back, Mark Catchpole has another question. I think you kind of covered this, but it'd be good to clarify. Can you measure across large surfaces, for example, 1 meter by 1 meter?
With the ProSurf, we made one special option for a client, and they wanted a 500mm stage to scan across the surface, and the weight of that part was 50 kilograms. That's the largest we made, but we have a special applications department. I would not necessarily say it's practical to do an image stitching over that area, simply because you start to end up with such huge amounts of data. It's really the challenge of data handling that becomes a problem there, because you can end up with unpractical sized data sets to manage. So it depends on what type of parameters you're looking for.
Thank you. The next one, Nick Morell. Can we measure corrosion defects in steel castings?
Sorry, can you repeat that question?
Yeah, of course. Can we measure corrosion defects in steel castings?
The microscope will allow you to measure small areas, and if you've got like scratches, if you've got small changes in texture on the surface, then you can get some very nice representation, and you can do image stitching where you can measure very small changes in the surface, very subtle changes. But sometimes some surfaces, such as maybe a castings, they're a much larger surface type. They maybe you've got a bearing and it has it's a large bearing with a low radii, and so you have a much larger area, and you want to see the global wear of the surface. Then the ProSurf can be very interesting for that, and you can get some really interesting tribology type measurements over large areas if you then consider the ProSurf. It has a slightly lower XY sampling rate, but if you want to see the generalized removal of material, then the ProSurf, the macro lens system, can be quite interesting. Of course, with these sort of wear scars, you tend to have a combination of both smooth, shiny, bright, dark, combination type surfaces, even carbonization on a surface. And we have a smart scanning capability where our technology can optimize the measurement performance for really sort of multi-light leveled surfaces. So we can get really good, strong, real data without the need of filtering or data filling.
Brilliant, thank you. Dean Mitchell has asked, which would you view the surface of paint or clear coats? For instance, looking for RA, RZ reading for scratches after sanding.
If you're measuring small features, then you'd be looking at the microscope. If you're doing shot blasting and you want to look at the wear mechanism of the shot, then you'd have to go and use a microscope. If you're looking for applications like roping, where you're looking at maybe orange peel effects or ripple, then those are low spatial frequencies. And at that point, the macroscope is preferable, just simply because you're measuring a larger area. And in fact, within the coal rolling industry, we have both our entry-level Metro Lab and our ProSurf addressing these applications in fully automated measurement and analysis environments. So they are popular applications for us.
Thank you very much. One other question, are you able to export the data for use with other systems?
Yes, you can export the data as various formats such as ASCII, .sur, .stl, so you can triangulate the data as well.
Thank you very much. Terry Hodson with another question. Are these items UK built?
They're all built in Europe, in Germany. Our parent company is in Waldbronn. It's in Bavaria, near the Black Forest. It's beautiful. The quality of the product is second to none. Here I am in Polytec Limited today. They are based and situated in Coventry, and of course we have an open house policy here where we're always welcoming and we'll always invite people to come and see our laboratory and our sort of equipment. And today we have 3 different topography tools standing next to me.
Brilliant, thank you very much. The next one, how do you measure beyond the diffraction barrier of light?
Well, this is all down to signal processing. If you're using a focus variation or a confocal system, then you can only squeeze and focus so much light through an objective lens. And you'll have a point where you have beam waste. And that beam waste gives you a measurement uncertainty, typically in the order of 10 nanometers. And it's worth considering that with those technologies, it's very easy to add a decimal point onto your Z resolution, but adding a decimal point is very easy to do. Whereas what we're doing is through the correlogram information, we look to the phase information, we signal process that information, so we have a fuller set of information to signal process, and that is how we can get down beyond the diffraction barrier of light. And it's all down to clever signal processing and algorithms, and this really is part of Polytec's IP.
Fantastic. Brilliant. The last question I have, obviously something else pops up, I will let you know. Can you measure the thickness of a surface?
If it's scratched and it's broken, then you can measure a step height. If it's a transparent surface and you get multiple interferograms on thick films or thick thin films, then you can certainly do that. And if it's got an edge, then you can measure an edge. So the answer is yes, but of course there are limitations when you come down to thin films.
Fantastic. Okay, I think that's all the questions we have for the time being. If anyone thinks of anything after this, feel free to get in contact with Joe directly. Contact details have been posted in the chat part. Thank you ever so much, Joe, for your time and for the presentation. Thank you also to everyone for joining. We will be back next week, I believe, with someone from VW. But as I say, it's always a pleasure, and thank you again.
Okay, thanks everyone for joining. Thank you. Bye bye.